A bowling ball of mass 7.1 kilograms and diameter 21.6 centimeters, and again they're giving us the diameter. What I probably want is the radius, so let's just right away say that the radius is 10.8, is thrown down the alley at a speed of 8.7 meters per second. The bowling ball is initially skidding with no angular velocity. So the initial angular velocity is 0. The coefficient of friction between the ball and the alley is 0.3 for static, and for kinetic, 0.25. So when the bowling ball is initially thrown, let's say time 1 is equal to 0, and r1 and theta 1 are both equal to 0, the initial angular velocity is 0, but it's thrown with a speed of 8.7 meters per second. This is rolling with slipping, so it is not true that the velocity is equal to r times omega initially. Event 2 is when the ball begins to roll without slipping. So at event 2, we will have V2 is equal to R times omega 2, but not before event 2. Now we need to do the free body diagram. I have the force of gravity acting downward on the object, that's the mass of the bowling ball times little g. I have the normal force that the floor exerts on the bowling ball, and I have a force of friction. Because the ball is rolling and slipping, actually initially it's just slipping and not rolling, a point here on the ball would be sliding on the surface, so this is kinetic friction because it is slipping. If it was rolling without slipping, then it would be static friction. So I'm going to start off doing Newton's second law. So I'll start with the sum of the forces in the y direction. In the y direction, the acceleration is equal to 0. That means the normal force is equal to m times g. And I can also use the coefficient of kinetic friction, multiply that by the normal force to get the force of kinetic friction, so that's mu k times mg. Now I'm going to look in the x direction. Sum of the force is in the x direction is equal to mass times acceleration in the x direction. I do have acceleration in the x direction, and that's going to be what I put in my table here. And I have one force acting in the x direction. It's acting this way, but let's say the positive direction for x is this way. So this force is in the negative direction, so I have minus FKF, which is equal to negative mu k mg, is equal to mass times acceleration in the x direction. So acceleration in the x direction is equal to negative mu kg. That has the correct units, and the ball is slowing down, so it's moving this way and the acceleration is this way. I know the coefficient of kinetic friction, so I can actually calculate that acceleration now. So this is negative 0.25 times 9.8 meters per second squared, and that gives me negative 2.45. This force of kinetic friction is acting on the ball from event 1 to event 2, so we have constant acceleration. So this is the acceleration at event 1 up until when the ball begins to roll with slipping. Okay, then we're going to look at the sum of the torques in order to find the angular acceleration. So Well, I've never done this before. We have Newton's second law for rotational motion. So in the past, the sum of the torques has been equal to 0, but now we actually have angular acceleration. So the sum of the torques is equal to the moment of inertia times the angular acceleration. And I'm going to use an axis which is going through the center of mass. And so the axis for the moment of inertia is going through the center of the mass. The bowling ball is a solid sphere. And so from page 60 we get the moment of inertia for an axis going through the mass center is 2/5 mr squared. So I is equal to 2/5. The mass of the bowling ball is 7.1. And the radius is 10.8 centimeters. Let's do this also. I don't want to use centimeters, I want to use meters. So this is 0.108 meters. And that's squared, so we have 2/5 mr squared. Let's just say that. Okay, times the angular acceleration. Now I have to look at the torque. Well, this force, the force of gravity, is acting right at the axis of rotation. So I'm going to get 0 for that torque because r is equal to 0. The normal force is acting like this, but the vector r, which goes from the axis of rotation to the force, is pointed in the opposite direction, so the angle that you have there is 180 degrees. Remember, the torque is equal to r times F times sine of the angle, so the normal force does not cause rotation. That leaves us just with the force of kinetic friction, which causes rotation in this direction. And this angle is 90 degrees, so we have r, which is equal to 0.18 times the force of kinetic friction. And then let me just say here, this is the direction of the angular acceleration, so I'm going to call that the positive direction for angular acceleration. And the force of kinetic friction is equal to mu k times mg. So I can put that in here. So I have 0.108. Mu k is equal to 0.25. The mass is equal to 7.1. And g is equal to 9.8. This is equal to 2/5 times 7.1 times 0.108 squared times the angular acceleration. The mass cancels out. One of these cancels with one of those. And I get the angular acceleration is multiply both sides by 5/2. And we have 0.25 times 9.8, and then divide by 0.108 to get the angular acceleration. And that is 56.7 radians per second squared. I guess I should also be finding the magnitude of each force. So for the normal force, I should plug in the mass. And I get 69.58. So the normal force is equal to m times g, so this is 69.58 newtons. And the force of kinetic friction, if you multiply by the coefficient of kinetic friction, you get 17.4. So we have all of our unknown forces. I now have my angular acceleration, which I can put in my table. I think this was supposed to be 56 0.7. So I can put that in my table. I showed here the direction for the angular acceleration, so I'm just going to say it's in that direction.